Good evening, everyone. Welcome to Unacademy, the largest online e-learning platform. Today, I'm going to discuss steady state error. It's a part of control system engineering crash course. So, before today's lecture 4, I would like to give you a glimpse of how to install Unacademy app. Before that, I'm Vice Shravan Kumar, having 7+ years of experience, mentored more than 5K students, and cracked GATE. Let's look at the Unacademy Learning App installation procedure. Go to Play Store, type Unacademy Learning App, and then you'll get this step 2 as install. Just install it. You'll get this GATE and ESE if you're opting for GATE and Engineering Services. Step 3 would be clicking on this GATE and Engineering Services, and step 4 would be clicking on this plus. Then you'll get something like Get Subscription. Click on this, and you can use my code as YSK10 to get maximum discount of 10%. You also have plus and iconic subscriptions. As I've been telling you, you'll get a separate mentor for you preparation in iconic subscription, and you can use my code. Then you have different types of payments: debit card, EMI, UPIs, wallets, net banking. There are so many other payment options that you have. You can go ahead with these payment options and pay the amount and get subscribed to Unacademy. Today's topics are, in brief, we'll discuss second order system response, error constant, and steady state error. So, first, let me consider second order standard system. Second order system. So, the standard second order system is given by this. They have a comparator. Let's consider a unity feedback system. This is C of S, input R of S. This is the error detector, and this is omega n square by s square plus 2 zeta omega ns. And let's consider a unity feedback system. Now if you are writing this is omega n square by s square plus 2 zeta omega n is the open loop transfer function, consider the closed loop transfer function. C of s by R of s is equal to, it is omega n square by s square plus 2 zeta omega ns by 1 plus omega n square by s square plus 2 zeta omega ns. How did you get this? For a feedback path, we know that it is g of s by 1 plus g of s into h of s. That's what I have written. I'll consider this as g of s and this as h of s. So h of s value here would be 1. So this part is g of s by 1 plus g of s into h of s. Now this comes out to be omega n square by, if we take LCM and cancel out, it is s square plus 2 zeta omega ns plus omega n square. This is a standard second order transfer function. So the standard second order transfer function is C of s by R of s is equal to omega n square by s square plus 2 zeta, sorry, 2 zeta omega ns plus omega n square, where omega n is undamped natural frequency in radian per second, and zeta is damping ratio. Now, based on value of zeta, systems can be classified as 4 types. One is if zeta value is equal to 1, if zeta is equal to 0, let us consider, and zeta is equal to 1, zeta less than 1, that is 0 less than zeta less than 1, and zeta greater than 1. Good evening, Ramu. Good evening, Ramchandra. So zeta is equal to 0 is an undamped system. Zeta is equal to 1 is a critically damped system. If the zeta value is between 0 and 1, it is under damped system. Hope you are getting my point. And if zeta greater than 1, it is an over damped system. So based on the values of zeta, you can classify the systems as undamped system, critically damped system, under damped system, and over damped systems. Now, hope this is clear. This is the standard second order system. Sorry. And these are based on the values of zeta. Systems are classified. Okay. So once again, the value of C of S by R of S is omega n square by S square plus 2 zeta omega ns, and based on the value of zeta, if zeta is equal to 0, it is an undamped system. Zeta is equal to 1, critically damped. Zeta is between 0 and 1, it is under damped system, and zeta greater than 1 is an over damped system. Now let us consider the response of second order system, which is undamped. You may be asked any question, and for step input, so it is response of undamped system, second order system for step input. Now let us see how to do that. First thing, input is step. That implies, in C of S by R of S is considered to be the input. So what is the value of R of S is equal to 1 by S, because it's a unit step input. Take it as an unit step input, so it is 1 by S. Instead of step input, you can take as unit step input. So you already know what is C of S by R of S. C of S by R of S is equal to omega n square by S square plus 2 zeta omega ns plus omega n square. So this is the input, and the second important point here is it is an undamped system. For an undamped system, if you see, for an undamped system, the value of zeta is 0. So the value of zeta here is equal to 0, damping ratio. Substitute these two conditions. So C of S is equal to omega n square by S square plus omega n square into R of S. You can also write it as omega n square by, I'll write in the next slide. Maybe it's not visible for you. So C of S is equal to omega n square by S square plus omega n square into R of S. This is what we got here. Omega n square by S square plus omega n square into R of S. Now what is R of S? R of S is 1 by S. Therefore, C of S is equal to omega n square by S square plus omega n square into 1 by S. Our task is, see here we are saying the response is nothing but time response. It is C of t. This is what we need to find. So here we have C of S. We need to find C of t. So let's take some partial fractions. You can write it as a by s plus bsc by s square plus omega n square. Only if you can do this partial fractions, you'll be able to apply inverse Laplace transform. And once you simplify this, you'll get the value of a as 1, b as minus 1. Partial fractions is very simple, and c as 0. So from this, you can write c of s is equal to Anup. Hello, sir. Hello, Anup. Good evening. You can write 1 by s plus minus 1 into s plus 0 by s square plus omega n square. Finally, you'll get 1 by s minus s by s square plus omega n square. From this, just taking this to the next slide. Yeah, this is what you got now. From this, you can write, you can apply inverse Laplace transform. Thank you, thank you. So apply inverse Laplace transform. So Laplace inverse of C of s is equal to Laplace inverse of 1 by s minus Laplace inverse of s by s square plus omega n square. Now we should look at the formulae. Laplace transform. Laplace of 1 is 1 by s. So Laplace inverse of 1 by s would be 1. And Laplace of e power at is 1 by s minus a. So the Laplace inverse of 1 by s minus a would be e power at. And the Laplace inverse of s by s square plus a square is equal to cos at. Or Laplace of cos at is s by s square plus a square. So if you apply the same here, what is Laplace inverse of 1 by s? It is 1. Minus what is Laplace inverse of s by s square plus a square? It is cos omega n t. So Laplace inverse of C of s is C of t. This is the response of a second order undamped system for unit step input. Similarly, if you try to draw a graph for this, take both input and output. Let's say this is the input R of t or R of s. So that is this step input. This is t, and C of t would be its 1 minus cosine is a waveform, something like this. This is t with respect to. So it is an undamped system. You'll get the oscillations. This is an undamped response. This is an undamped response. Similarly, you can apply the same procedure and find the response of second order system for overdamped system and step input, or any input that for that matter of consideration. You can consider any input, or an underdamped system, because this being a crash course will not be able to derive all the things, or a critically damped system for the same inputs or a different input of your consideration. So let's look at this once again, what I have done. So first we have considered a second order system, and from this standard second order system we have got the second order system transfer function C of s by R of s, and based on the value of zeta they are classified as 4 undamped, critically damped, underdamped and overdamped systems. And for these you can find the response C of t for R of s any input. Basically we are considering a step input. So we have taken up the response of second order system, undamped system, for a unit step input. So we have taken C of s by R of s as the in transfer function, and R of s is 1 by s because input being step, we have considered this. And second is because this being an undamped system that we have considered, undamped system, thank you Satish, undamped system zeta is equal to 0. Now if you substitute both these conditions 1 and 2 in this, so you'll place 0 in place of zeta, and so you'll get omega n square by s square plus omega n square into R of s. So we have taken R of s to the other side. Now what is R of s? R of s is 1 by s. We substitute the value of R of s. Then in order to find its response C of t, we need to take the inverse Laplace transform. So for that we require the partial fractions. So I have taken a by s plus b plus c by s square plus omega n square. Once you try to find the values of a, b, c, you'll get 1, minus 1 and 0. And when you take the inverse Laplace transform to this, you'll get c of t as 1 minus cosine of omega n t, and this will be the input of the considered system, and this is the output. Hope this part is clear, and for this you need to be clear with this uh, Laplace transform equations. You should be familiar with this Laplace transform formulae. Good evening Shiva. So in this, next we will consider, so that was all about the response of a second order system, and now we'll consider steady state error, and we'll also discuss error constants. Steady state error and error constants. I'm sorry. So steady state error, it is denoted by ESS, and it measures the accuracy of the system, and it is, if you consider a response of the system, let us consider a small underdamped response so that that will be very easy for you. Let's say this is C of t, and consider an underdamped response which is generally like this, and let the input be this. Now this difference at t is equal to infinity is the steady state error. This is the error. So it is nothing but e of t at t is equal to, or t tends to infinity. Good evening SR. So in order to find what is this error, now we need to consider the same closed loop block diagram. So let us call these, so let us consider this. Let this be R of s. This is error detector, so it is output of it is E of s, and the output is C of s, and forward path is G of s, and feedback is H of s. So let us consider this and find an expression for error. So from this, what can we write the expression of E of s? Can someone tell me what is the expression for error E of s is equal to? It is R of s, if this is minus and this is plus. See, if you take this and this is E of s, and here you have something as an input, and these things are, this is R of S, this is H of S into C of S. This is right. C of S, a part of the signal is given back to the H of S, and that is given again to this error detector. So what would E of S be? It is R of S if this is plus and this is minus, negative feedback if you are considering, R of S minus H of S into C of S. So that's what I'm going to write. E of S is equal to R of S minus H of S into C of S. But we know that if you look at this, what is C of S? It is E of S into G of S. So C of S is equal to E of S into G of S. So substitute this in this equation. So you can write it as E of S is equal to R of S minus H of S, in place of C of S, write E of S into G of S. Now because these two terms, this and this has E of S, and we need to find that E of S, I'm taking this term to the left hand side. So E of S plus H of S into G of S into E of S is equal to R of S. I'll take this to the next slide. So this is the expression that we got till now. Now what is our task? Our task is to find E of S. What is E of S is equal to, if you take common E of S here, just take common E of S to the other left side. E of S, if you are taking common, it is 1 plus G of S into H of S is equal to R of S to the right side remains same. Very useful. Need step by step explanation. Thank you. Srinath, good evening. Thank you, yes, sir. So E of S is equal to R of S by 1 plus G of S into H of S. So this is the expression for error. So this is the expression for error E of S. Now we need to find steady state error ESS. So for this, first you need to know some of the basics of mathematics, like so before that I'll just discuss what we have done just now. I'll just go back. We'll see what is steady state error. It is generally denoted by E of S. It's a measure of accuracy, and it is E of t at t tends to infinity. If you consider an under damped system, you'll be clearly able to see this error. And we have considered this block diagram, and from this we have derived this E of S, where E of S is the difference of R of S and H of S and C of S. From there we got the expression for E of S. We have simplified this, and at the end we got E of S as R of S by 1 plus G of S into H of S. Now, now let's consider we need E of t. What is E of t? It is Laplace inverse of E of S, simply. So what is steady state error? So the steady state error ESS, steady state error is equal to, it is limit t tends to infinity E of t. This is what is error, right? E of t at t tends to infinity. So mathematically, limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. This is a final value theorem. Similarly, you can write it as ESS is equal to limit s tends to 0 s into E of s. So we'll take this to the next slide and write an expression for ESS. Therefore, ESS is equal to limit s tends to 0 s into what is E of s? It is R of s by 1 plus G of s into H of s. This is the expression for steady state error. Nagesh, good evening, sir. Good evening. So once again, ESS is the steady state error, which is the error at t is equal to infinity. From final value theorem, limit t tends to infinity, f of t is equal to, I'm sorry, limit s tends to 0, s into f of s. So ESS is equal to limit s tends to 0, s into E of s. So therefore, ESS is equal to limit s tends to 0, s into R of s by 1 plus G of s into H of s. Hope this steady state error expression is clear for everyone. Nice teaching, sir. Go ahead in this fashion. Thank you. Augustus, good evening. Thank you, sir, for neat explanation. Thank you, Augustus. So with this expression of steady state error, good to see you all again for this lecture on steady state error. Hope this is an useful session for you all. So with this expression of steady state error, so this is steady state error expression. Now we have to see some of the constant. This steady state error can be a zero value or can be a constant and can be infinity. And this depends upon basically the type of the system. So first I'll write G of s into H of s for different types of systems. Then we will find steady state error for different inputs and different types of systems. Now let us consider G of s into H of s. G of s into H of s is equal to s plus, because the numerator are zeros, s plus z1 into s plus z2 and so on by s, sorry, s plus z1 into s plus z2 by s plus p1, denominator are called as poles, s plus p2 and so on. Now in this, if you see, this is a type 0 system. Must be very careful here. It's a type 0 system because there are no poles at the origin. Now for type 1 system, if you look at type 1 system, G of s into H of s is equal to s plus z1 into s plus z2 and so on by, it is s into s plus p1 into s plus p2 and so on. Similarly, if you write for type 2 system, what is G of s into H of s written as? It is s plus z1 into s plus z2 by s square into s plus p1 and so on into s plus p2 and so on. Now let me give you a brief idea about this. Type 0, there is no pole at the origin. Here you don't find any s simply. And type 1 system, you have one pole at the origin. So this is a type 1 system. Type 2 system, you have two poles at the origin. These are not the poles at the origin. These are the poles at some different location. Karthik Jilla, good evening, sir. Good evening, Karthik. So you have type 0. This is type 1. And this is type 2 system. So once we are clear with this type 0, type 1, type 2 systems, we will find steady state error for different inputs. So let's take this expression. You need these expressions. Sorry. So this is Now we are going to see steady state error per unit step input. We'll see for once we get this, we'll see for the different types of the systems again. First, we'll consider one input. Now, let us consider what is ESS. So, ESS is equal to limit s tends to 0 s into r of s by 1 plus g of s into h of s. Good evening. Now, for step input, what is the value of r of s? R of s is equal to 1 by s. So substitute the same here. So E of ESS is equal to limit s tends to 0 s into r of s is 1 by s by 1 plus g of s into h of s. Now if you see here, you can cancel these two. So if you apply limit, you'll get 1 by 1 plus, limit can be applied to this, limit s tends to 0 g of s into h of s, and this term is called as, you are not able to see this, this is the expression, and this is given as 1 by 1 plus kp, position error constant, 1 by 1 plus kp, where kp is called positional error constant given by limit s tends to 0 g of s into h of s. Everyone has to remember this. This is very important. You'll have to solve problems based on this values of steady state errors and error constants. This is one of the important topics which will appear in your semester examinations, wherein you'll be asked to find the error constants as well as steady state error. Mahesh Kusma, good evening. Good evening, Mahesh Kusma. So once we know this ESS and KP values, so this is ESS. Steady state error for step input is 1 by 1 plus Kp, where Kp is equal to limit s tends to 0 g of s into h of s. Now, this value of ESS will have a 0, infinity, and a constant value based on the type of the system. Now, what is the type of the system? First, we have already discussed. Sorry, पानु सर हिंदी में चाहिए प्लीज, या आई ऑल्सो, मैं हिंदी में भी बोल दूंगा. स्टेडी स्टेट एरर फाइंड कर रहे हैं, प्रॉब्ली फ्रॉम द नेक्स्ट क्लास आई ट्राई टू हैव बोथ हिंदी एंड इंग्लिश. फॉर नाउ जस्ट वी आर डिस्कसिंग इट. चलो मैं आपसे बोल दूंगा कि स्टेडी स्टेट एरर फाइंड कर रहे हैं, कैसे फाइंड करना, आई जस्ट टेल यू दैट. अगर आप लिए तो यहाँ पे स्टेडी स्टेट एरर की वैल्यू जो है ना, यहाँ पे 3 वैल्यूज हो सकते हैं, 0, इन्फिनिटी और के, कांस्टेंट हो सकती है. ये कैसा पता चलेगा? व्हेन यू आर सब्स्टिट्यूटिंग द टाइप ऑफ द सिस्टम. अगर टाइप की बात करें तो हम जी ऑफ एस और एच ऑफ एस लिख दिए थे टाइप ऑफ द सिस्टम. अगर टाइप जीरो सिस्टम ले लिए तो इट इज एस प्लस जेड वन इंटू एस प्लस जेड टू बाई नाउ एस प्लस पी वन इंटू एस प्लस पी टू. So this was for the type 0. So let's find steady state error for type 0 system. अगर हम type 0 system ले लिए तो, now let's see what is Kp first. Kp is equal to limit s tends to 0 g of s into h of s is s plus z1 or s plus z2 or so on. यहाँ पे भी रहते by s plus p1 or s plus p2 लिख सकते हैं यहाँ पे. So then अगर आप s is equal to 0 लगा दिए ना यहाँ पे, if you substitute s is equal to 0 here, 0 here and 0 here, यहाँ पे भी 0 लगा दिए तो you'll get a constant value, right? And if you write ESS is equal to 1 by 1 plus KP, अगर KP constant value है तो ESS भी constant value ही रहेगा, right? So this is steady state error for step input. Now if you take step input type 0. Now if you're taking type 1 system, let us consider type 1 system. लिख देंगे यहाँ पे ESS की वैल्यू क्या है, 1/1 प्लस KP है, और व्हाट इज KP क्या है यहाँ पे, KP इज इक्वल टू लिमिट S टेंस टू 0 और G ऑफ S इंटू H ऑफ S. तो अब हम क्या कर रहे हैं, यहाँ पे टाइप 1 के रेस्पॉन्स ले रहे हैं. टाइप 1 स्टेप इनपुट. व्हाट इज टाइप 1 सिस्टम, लेट्स राइट दैट. लेट्स राइट G ऑफ S इंटू H ऑफ S फॉर टाइप 1. G of S into H of S is S plus Z1 or S plus Z2 and so on by, क्या लिखते हैं यहाँ पे, S into S plus P1 और S plus P2 and so on. How is this a type 1 system? Because यहाँ पे जो पोल है ना, यहाँ पे एक जीरो है, जीरो का नहीं है पोल. दिस इज देर इज अ पोल एट द ओरिजिन. देर इज अ पोल एट द ओरिजिन के पास एक पोल है. सो इसकी वजह से इसको क्या बोलते हैं, टाइप 1 सिस्टम बोल के बोलते हैं. Now if you try to find the KP value from this, you just try to find KP. KP is equal to limit S tends to 0, G of S into H of S, S plus Z1, S plus Z2 by S into S plus P1 and S plus P2. Now when you substitute at the rest of the places, it does not matter, but when you take S is equal to 0 here, the KP value will be infinite. Right, 1 by 0 is an infinite value. अगर KP की वैल्यू infinite है, ESS की वैल्यू क्या होगी, 1 by 1 plus KP. KP is infinity, so ESS value would obviously be 0. So this is the steady state error for type 1 system step input. Hope this is clear. Type 1 system and step input steady state error is 0. So let's take the other one. This was for steady state error for unit step input. Now let's take steady state error for, let's write steady state error for ramp input. The ramp input or unit ramp input. Steady state error for unit ramp input. So first write what is ESS. ESS is equal to limit S tends to 0, S into R of S by 1 plus G of S into H of S. Now फर्स्ट स्टेप इनपुट हो गया, अभी रैंप इनपुट के बारे में कर रहे हैं. व्हाट इज रैंप इनपुट, फॉर रैंप इनपुट क्या है वो, फॉर रैंप इनपुट व्हाट इज आर ऑफ एस इज इक्वल टू, इट इज 1 by s square, right? For ramp input it is 1 by s square. Now if you substitute it, what is ess is equal to limit s tends to 0, s into 1 by s square by 1 plus g of s into h of s. You can cancel out 1s here, और क्या आएगा यहाँ पे, लिमिट s tends to 0. I'll just write it upwards so that it will be clear for you. ये यहाँ पे लिख रहा हूँ. So it is limit s tends to 0, 1 by s plus s into g of s into h of s. इसको क्या लिख सकते हैं, लिमिट s tends to 0, I'm sorry, yeah, limit s tends to 0, 1 by s. Let's take to the next slide else. यहाँ से ले लेंगे to the new page. चलो, now you have this, right? Now you have this steady state error. Now from this what can you write, ess is equal to 1 by limit s tends to 0, s plus limit s tends to 0, s into g of s into h of s, right? यहाँ पे एक s थी, यहाँ पे मल्टीप्लाई हो गई, यहाँ पे मल्टीप्लाई हो गई. Now when limit s tends to 0, this value is 0, right? So this is 1 by limit s tends to 0, s into g of s into h of s, if you take it. Now this is written as 1 by, this is called as 1 by kv, velocity error constant. kv को क्या बोलते हैं अपन, velocity kp क्या था, it's a positional error constant, and kv is velocity error constant. kv is velocity error constant. Now with this of kv and ess is 1 by kv, and kv is equal to limit s tends to 0 s into g of s into h of s. So with these values, let's find what is steady state error for different type of systems. Now let's take this to the new slide. So this is steady state error and kv value, that is steady state error for ramp input. So let's consider the types of the system. अगर अपन टाइप जीरो सिस्टम ले लिए ना, टाइप जीरो सिस्टम लिए तो what is g of s into h of s, as I have already told you, it is s plus z1 into s plus z2 and so on by s plus p1 into s plus p2 and so on. This is a type 0 system. Now let's find what is kv value for that. Now limit s tends to 0 s into s plus z1 into s plus z2 and so on by s plus p1 into s plus p2 and so on. If you substitute s is equal to 0, what is the value of kv? Kv is 0. What is steady state error? 1 by 1 plus kv, 1 by 0 would give you infinite. So for a type 0 input, ramp will give steady state error of infinity and kv value of 0. For a ramp input type 0 system, steady state error is infinity and kv value is 0. Hope this is clear for you. Now let us consider type 1 system ramp input. So we'll take the same. So this was the steady state error and kv value for ramp input. Let's write sorry, type 1 system. अगर टाइप 1 सिस्टम लिए तो व्हाट इज जी ऑफ एस इंटू एच ऑफ एस क्या है वहाँ पे, इट इज एस प्लस जेड वन इंटू एस प्लस जेड टू एंड सो ऑन बाई एस इंटू एस प्लस पी वन इंटू एस प्लस पी टू एंड सो ऑन. अगर अब हम अभी केवी की वैल्यू फाइंड करें, व्हाट इज केवी इज इक्वल टू लिमिट, लेट्स फाइंड केवी वैल्यू. केवी इज इक्वल टू व्हाट, limit s tends to 0. देखो यहाँ पे s into g of s into h of s. So s into, what is g of s into h of s, this value, that is s plus z1 into s plus z2 by s into s plus p1 into s plus p2 and so on. So you can cancel out this s and this will give you a constant value if you substitute s is equal to 0. Therefore ess is equal to 1 by kv. If kv is a constant, ess is also a constant value. So this is how you'll find the steady state error for ramp input type 1 system. Hope this is clear for everyone. Now let us consider steady state error steady state error. Now let's also do the type 2 system for ramp input. Let us take this to the next slide and do it also for type 2 system. Then we'll understand what's the value exactly. Now let's find ESS for type 2 system. Let's write type 2 system first. I'm sorry. G of s into h of s is equal to s plus z1 into s plus z2 and so on by s square into s plus p1 into s plus p2 and so on. ऐसे लिख सकते हैं. Now first find kv value. kv is equal to limit s tends to 0 s into s plus z1 into s plus z2 by s plus p1 यहाँ पे s स्क्वायर भी है एंड s प्लस पी टू एंड सो ऑन. ना अगर आप s और s कैंसिल कर दिया और एक s बच गया यहाँ पे, so limit when s tends to 0 kv value will be something by 0 would give you an infinite value. So here steady state error in this case is 1 by kv, which is 1 by infinity is 0. Now for type 2 system, steady state error is 0. Now let's look at the type 1 system. Steady state error is a constant value, and for type 0 system, steady state error was an infinite value. Here steady state error is infinite, and this is a constant, and this is a 0 value for type 0, type 1, type 2 system and ramp input. Similarly, let's look at steady state error for parabolic input. You can do it in the similar way as we have done for. I just want at least one of you or two of you to just do it and tell me what are the values of a steady state error, and if you have any other constant, what is the constant that you come across. Now for parabolic input, let us take the parabolic input as r of s as 1 by s cube. Now what is ess is equal to limit s tends to 0 s into r of s by 1 plus g of s into h of s. अगर अपन यहाँ पे एस आर एफ एस की वैल्यू लिख दिए ना, इफ यू कैन राइट आर ऑफ एस एज 1 by s cube, so limit s tends to 0 s into 1 by s cube by 1 plus g of s into h of s. Now if you cancel out one s here, you'll have s square here, so it is limit s tends to 0 1 by s square plus s square into g of s into h of s, g of s into h of s. Now what would be ess then? Ess is equal to 1 by, if you apply limit to this s square, it is 0, so it is limit s tends to 0 s square into g of s into h of s, and this is written as 1 by ka, acceleration error constant. Ka is equal to limit s tends to 0 s square into g of s into h of s. So these are the values of ess. ess की वैल्यू हो गई 1 by ka, और ka की वैल्यू हो गई लिमिट s tends to 0 s square into g of s into h of s. Now हम अभी you have to find these ess and ka की वैल्यू फाइंड आउट करने पड़ेगी different types of the system. So let us take this to the next slide, and this is steady state error and acceleration error constant. I did not write that. Let me tell you, ka is called as acceleration error constant. Now for type 1, I'm writing directly, just try to understand. So ka की value होती है limit s tends to 0 s square into g of s plus z1 into s plus z2 and so on by s plus p1 into s plus p2 and so on. This is type 0 system. You don't have any pole at the origin. If you substitute s is equal to 0, what would be the value of this? This is 0. Therefore, what is ess is equal to 1 by ka. That is 1 by 0 is infinite. Now let us take type 1 system. Let us take, this is, sorry, this is type 0 system. I'm sorry, this is type 0 system. So you don't have s here. Now let's take type 1 system. The ka value will be limit s tends to 0 s square into s plus z1 into s plus z2 and so on by s into, this is type 1, the previous one was type 0. There was a small change, this is type 0 because you don't have any pole here. Now you have a pole, you'll cancel out this, even then you'll get ka value as 0. Therefore what is steady state error again? 1 by ka is equal to 1 by 0 is infinite, Now let's consider this and find type 2 system. Now for type 2 system, let us consider type 2 system. Type 2 system. Type 2 system. Type 0, type 1 we have done. So Ka is equal to limit s tends to 0, s square into s plus z1 into s plus z2 and so on by type 2 s square into s plus p1. Type 2 means s square, two poles at the origin, so s plus p2 and so on. Now these gets cancelled out and this value will be a constant value, so therefore ess will be 1 by Ka, because Ka is constant. This is also a constant value. So this is how you'll find. Yeah, I'll repeat this once again, don't worry, because this being a crash course I just have to want to complete the topic. So maybe I'm being bit fast. I'll just try to slow down and I'll also explain you once again. Just we'll just move back and we'll see what we have done from steady state error. Yeah, now look at this, we'll see one by one once again. So we have considered steady state error and error constants. ESS is the steady state error and E of t is the error at t is equal to infinity, and we have considered a block diagram, and from this block diagram we have tried to find out what is E of s. For an underdamped system you can see this is the error. So we have considered E of s, which is the difference of R of s and C of s into H of s. So we have obtained this E of s is equal to R of s minus H of s into C of s. From this we have written what is C of s here, which is E of s into G of s. Upon simplification you got an expression for E of s, which is R of s by 1 plus G of s into H of s. But from final value theorem we know limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s. So ESS is limit t tends to infinity, or ESS is equal to, we can also write, instead of this you can also write this s into f of s, so s into E of s. So we already know the expression of E of s, just substitute it here. So E of s is equal to limit s tends to 0 s into E of s. E of s is R of s by 1 plus G of s into H of s. So either E of s value steady state error can be 0 or a constant, or there may be a large difference or infinite, and that would depend upon the type of the system basically. So agar first we'll speak of this type of the system, type 0. For type 0 system you do not have any pole at the origin here, you don't have s basically. For the type 1 system you'll have one s in the denominator. These are the zeros in the numerator and these are the poles at some other location other than the origin, and wherever the pole, if the pole is at the origin it is considered to be the type. So here you have one pole at the origin, so it is a type 1 system. Here you have two poles at the origin, so it is considered to be the type 2 system. So these are basically type 0, type 1 and type 2 systems. You made it very easy, thank you Karthik. So we have considered steady state error for unit step input. So we already know this expression for steady state error. ESS is equal to limit s tends to 0 s into R of s by 1 plus G of s into H of s. What is this R of s by 1 plus into H of s? This was E of s, right? So for step input R of s value is 1 by s, right? For R of s 1 by s, if you substitute, you already have an s here and 1 by s will cancel out. So from this if you apply limit, you cannot apply limit to 1 and 1, there is no s term, so that will remain 1 and 1. And if you apply limit to this term, it is limit s tends to 0 G of s into H of s. So this term is termed as the positional error constant. So it is positional error constant basically. So it is 1 by 1 plus kp denoted by kp, positional error constant. So ess will be 1 by 1 plus kp. And we we are to find kp value and ess value for different types of inputs, because g of s and h of s will change. G of s, H of s is different for different types of the systems. so that kp value will also change, and as kp value changes, ess is dependent on kp, so ess value will also change. So based on g of s into h of s, kp value will change, and in turn ess value will be changed. So for different types, g of s and h of s is different, so we are considering type 0 first. For that, g of s into h of s is s plus z1 into s plus z2. By substituting it here and applying that limit, you'll get a constant value, because if s tends to 0, you'll only remain with z1 z numbers, that is location of zeros and poles. If this is a constant, obviously be, because kp is a constant value, also be a constant value. So for type 0 system, step input ess is constant and kp is also a constant value. Now considering the type 1 system, if you go for the higher order, so this is the type 1 system, because you have one pole at the origin. Now when you substitute it in kp, that is if you substitute it here, g of s into h of s, so this s will become 0. So when this s is 0, kp value will tend to infinity. So when kp is infinity, 1 by 1 plus kp will give you 0. So the steady state error is 0 for type 1 system and step input. So if you go for the higher order type 2 and so on, the same values will you'll obtain it at the same values. Now we put where r of s will change, where r of s is 1 s into r of s will give you 1 by s again. So here you'll get a s term when you apply limit. So this is becoming 0. So this is written as 1 by limit s tends to 0 s into g of s into h of s, which is called as the velocity error constant. So this is the expression for velocity error constant. So steady state error will be 1 by kv. And similarly, because g of s and h of s is different for different types of the system, therefore kv will change and ess will change, and therefore we got type for type 0 system, kv value will be 0 and ess will be infinite. Similarly, for type 1 system, you'll get the constant values of kv and ess, and for type 2 system, you'll get the same infinity and 0. And similarly, we have done the steady state error for the parabolic input, as we have done for the step and ramp inputs. So hope this is clear. So today what we have discussed is the response of second order system, and we have discussed undamped case, undamped response. You can also have critically damped, underdamped, and the rest of the things. We have also seen what is a steady state error and error constants as well. The steady state errors were error constants were kp, kv, and ka. It s tends to 0, g of s into h of s, and steady state error was 1 by 1 plus kp, and velocity error constant was limit s tends to 0, s into g of s into h of s, acceleration error constant limit s tends to 0, s square into g of s into h of s, and ess is equal to 1 by kv velocity error constant, and it is acceleration error constant. So this is basically. So these are the things, these are the takeaways from today's session. A response of a second order system, and steady state error and error constants, position, velocity, and acceleration error constants. Mostly you'll be given a numerical on this, which we'll try to solve in some special sessions or some other session. So or the response of second order system under damped system. So hope this was an useful session for you. Please do join Sanvita. Good evening, sir. Good evening. I request you to please subscribe and like or share, and do continue to listen to my lectures. Control systems, it's one of the interesting subjects, and you can easily score good marks in your semester